Okay, so our next speaker is Nathan Klein. Nathan is a PhD candidate at Brigham Young University working on germination prediction models using soil climate data in the Great Basin. Nathan and his collaborators propose to use seedbed soil moisture and temperature conditions to guide plant material selection for post-wildfire vegetation. So please welcome Nathan.
Well, thank you very much. I first want to acknowledge my co-authors, Bruce Roundy. Most of the soil moisture and temperature data that I used to predict germination comes from his soil moisture and temperature stations throughout the Great Basin. You can see all the dots on there represent locations where he's installed those. Stuart Hardigree provided much of the germination data that we used to create these germination models, and definitely want to thank them. So we predicted germination in 11 plant revegetation species and in cheatgrass using soil moisture and temperature at 31 locations throughout the Intermountain West in the sagebrush steppe ecosystem. Most of the most of the stuff I'm going to talk about today is from the woodland sites. So that includes a western juniper, 5 western juniper communities. We've got 4 pinyon juniper communities down in Nevada, and there's 4 mostly juniper communities in Utah. 2 of the sites do have some pinyon in them. The outline of my presentation will follow. I'll first start with a comparison of plant materials. Then we'll talk about a comparison between those 3 woodland communities, and then I want to discuss the characteristics of the influence, site characteristics that influence germination prediction. So I'm going to jump right into this. This is the, oops, sorry, I pushed the wrong button. There we go. All right, so these are the plant materials that I'm modeled germination for, our prediction models are for. We've got 8 accessions of cheatgrass, crested wheatgrass, Snake River wheatgrass, blue bunch, squirreltail, big squirreltail, sandbergs, basin wild rye, flax, yarrow, lupin, and Nicholson sumray. Across the top, we've got the 4 seasons, and I split spring up into early and late spring as well. And if you look, these are percent of seasons where we predicted germination. I'll tell you how I predicted germination in a second. But these are the percent seasons where we predicted germination. As you can expect, the summer and the winter, we don't get a lot of germination. Whereas in the fall and in the spring, we have a lot more germination, a lot more seasons where we predict germination. So if germination was the end goal, then that table would have been all that you needed to see from my presentation, but it's not. As Val Anderson said yesterday, our goal is establishment, and so I just drew this kind of conceptual diagram real quick. Germination, showing germination timing up here on this flat line at the top of the diagram A, and then root growth down to some theoretical location, soil depth where root growth needs to be for a seedling to establish. And in well-adapted plant materials, the seed will germinate and grow their roots before the soil drying front overtakes the root. If it doesn't, like over here, the soil drying front overtakes root growth, then the seedling the roots would desiccate and the plant would die. So we want to be the well-adapted of the seedlings to outrun the soil drying front. Okay, so let me tell you how we're predicting germination. So, sorry, keep hitting that button. So we've developed this index that we call seasonal progress towards germination, and that's simply we're simply predicting the fastest 50% of seeds to germinate using a wet thermal time model. And so we've measured in a growth chamber, an incubation chamber, we measured the fastest, how long it takes a population of seeds, the fastest 50% of those seeds to germinate. So when you reach number 1, then we would predict that you would have germination. Anything above that is simply just more germination. And so as the first thing you notice is that cheatgrass does really well. Most of all of the other plant materials we have here also are germinating in the early spring. That's March and April in our woodland communities. That's what we would predict. Basin wild bride gets the short end of the stick here. It's not doing quite so well. It's probably because the temperatures are still cooler in March and April. If we look at late spring, Basin wild bride does a little better, almost there, not quite to one where we would predict that the fastest 50% of seeds would germinate. So I'll look at total spring. So this is March through June, and Basin wild bride finally makes it to where we would say that at least 50% of the seeds are going to germinate. Well, that takes us back to the establishment question, where once you germinate, you still have to grow your roots before the soil dries. And so some of these not so fast germinating plant materials may not have enough time to extend their roots to establish. Also, just real quick, you look at comparisons, and Northern crested wheatgrass germinates just about as well as blue bunch. I just really wanted to kind of group things together, so I did a group comparison of cheatgrass versus perennial grass and forbs. Again, we've got seasonal progress towards germination on the y-axis. And again, everything's germinating. Cheatgrass has significantly more seasonal progress towards germination than perennial grasses and forbs. I was a little curious to see what would happen if I took out Basin wild rye, and it moved it up to 6.75, but the difference was still significant in the favor of cheatgrass. So on to our woodland communities comparison. Our western, this is for spring again. Our western juniper communities had significantly more progress towards germination compared to the other two communities. This juniper pinyon community is the Utah communities, and the pinyon juniper is the Nevada communities. And I think that probably is a result of elevational differences. These communities are at a higher elevation than the western juniper communities that we're measuring, and so I think that's affecting thermal time. So I wanted to look at site characteristics and see which of the site characteristics are having the strongest influence on germination. And so we looked at elevation, solar radiation, precipitation, air temperature, and slope. And we use them to explain the variation we see between the different plant materials. And the thing to look at in this ordination, this is a conical correspondence analysis, is the length of the arrow indicates the level of influence that the characteristic has. So elevation, solar radiation, and precipitation were the strongest influences we had through March through June. at 27 of the locations in our network. So that included not just the woodland locations, but sagebrush and crested wheatgrass sites as well. If we break that down into sagebrush and grassland sites and woodland sites, the first thing I notice is that solar radiation has dropped out. So this solar radiation is, we developed that variable by using a digital elevation model and use the ArcGIS solar radiation tool to see how much solar radiation the sites were receiving. Well, solar radiation drops out of both of these individually, so that tells me that solar radiation is a difference, and that makes sense. There's community structure differences between the two, and but that also begs the question to me is what kind of effect is solar radiation having on progress towards germination, and in light of what Jeremy just talked about with cold temperatures and some of Chad Boyd's work on blue bunch freezing, I wanted to quickly look at the number of freezing days in a seed bed throughout, and this is throughout, well, we've got sagebrush and crested wheatgrass sites on the left and woodland sites on the right. And we can see that this is not a direct comparison. There are different experimental designs, but I wanted to show it to you anyway. In the spring and September, for sagebrush and crested wheatgrass communities, they're getting about 12 to 15 freeze days. In the woodland, it drops to about 5 days each. In the winter, sagebrush communities get about 70 freeze days, and in woodlands, that drops to just below 50 freeze days. And so that could be important when considering woodland encroachment, tree infilling, and establishment of native plants. So just some take-home messages. Some of the species are not ideal for some locations based on our progress towards germination modeling. Late germinating plant materials may not be ideal for outrunning the soil drying front. And some of the work that we're trying to do, not just me, but several of us down at Brigham Young University, we're characterizing the seedbed and the root zone. We've been developing these thermal time germination models. Kurt Young's been working on developing seminal root growth models, and we want to combine these into developing establishment, comprehensive establishment model where we can help direct plant material selection in post-wildfire revegetation efforts. Thank you.